Hello, I'm Anthony Botelho, and this is work that was done in collaboration with my colleagues Ethan Prehar and Neil Heffernan. And what I'm going to be talking about today is basically a set of analyses that were run that observe untrained recurrent models. So basically, these are deep learning models where a large portion of that model is basically randomized or left untrained, which is itself maybe this kind of unintuitive thought, as many of you are probably very used to spending a lot of time training your deep learning models for those of you who apply them. But before jumping into that main focus, it's important to just kind of remind you all about just neural network structure. So bear with me as I kind of give this very high level refresher here. So if we have a simple neural network here with three layers, the bottom layer, of course, is our set of features. So something that we've recorded, maybe these are actions or something that's been recorded from a learning platform. And in that hidden layer, we are kind of learning sets of representations of those features. So the model learns how to kind of combine those features and find interactions and expand them and do kind of interesting things in order to kind of generate this kind of rich feature vector that describes those initial kind of raw features in various different, more complex ways. And then of course, then our output layer, the one node at the top in this example, is just kind of taking those composite features and trying to map them onto some output. So in terms of model structure, we end up with that kind of bottom set of layers. So all of our hidden layers and the input layer, basically just learning sets of features and interactions. And then the output layer, the final layer, the single layer at the top, is effectively just a logistic regression or linear regression or some kind of regression that is learning how to map the generated features, the rich features of our hidden layer, and mapping those onto our dependent measure. And of course, there's been a lot of examples of how this hidden layer might be utilized in different contexts. In image processing, this hidden layer might be extracted in order to observe certain visual features that are learned, perhaps learning detecting lines or shapes in order to, say, build this cat detector that we have here. In natural language processing, the hidden layer is used often as a kind of a language embedding, or basically representing words or phrases or sentences. So if any of you are familiar with a lot of natural language processing, I'm sure there are a lot of papers here that are talking about or utilizing word embeddings. So that might be able to help, again, represent words and language. And also in educational contexts, it's been kind of recommended that we might be able to use the hidden layer of these units, say, in a knowledge tracing model, kind of referencing the deep knowledge tracing paper from Peach et al., which showed that maybe you can use this hidden layer to represent student knowledge state. So it's this kind of large, somewhat uninterpretable, but maybe still useful kind of latent representation of what a student knows at any given time. So conclusion, of course, is neural networks learn rich, high-dimensional features in that hidden layer that can be used as deep conceptual representations. We have a lot of examples of this being done, but the question actually still remains of, do they actually learn these deep conceptual representations of the data? Again, a lot of examples, but how deep and meaningful are these features that are being learned? Well, as it turns out, prior work by Wading and Keela in 2019 found that untrained recurrent models, again, a little unintuitive, untrained recurrent models could perform nearly as well as trained versions in natural language processing tasks. So even though we have examples where deep word embeddings can learn relationships between words, if you don't train part of your model, you end up actually with kind of similar performance when in comparison to when you train it. So again, intuitively, the idea here is you wouldn't train the bottom portion of your model, the important part that I highlighted earlier that's doing all of this kind of rich feature learning. It's learning how to combine your inputs and create these very complex interactions. And especially if we're thinking of like a recurrent model, this is also creating features of kind of temporal features over time. So if we don't train that and just initialize all of those weights to random values, and then just only train the top part, basically applying a logistic regression to a random feature generator, you get almost the same performance on a number of tasks. And it was also found in 2019 from Ding and Larson at the EDM conference that they also found that untrained recurrent models could perform nearly as well as trained versions of knowledge tracing. So from that paper in this table, you can see that their untrained model got a 0.73, and that's compared got a 0.73, and that's comparable to the DKT paper, which reported a 0.75, a replication of that work that was presented in Shang et al., which also reported BKT to have a 0.63. So actually, the untrained LSTM here is doing better than the than Bayesian knowledge tracing, which again was utilized for decades and has been a model of comparison for a long time. So in this paper, basically we wanted to do three things. We want to examine this idea, this kind of counterintuitive idea of using untrained deep learning models in another context. So we've seen it now being used for knowledge tracing in education. It was used in some NLP tasks. So let's try it in one other context and see, is there actually a trend here? So we decided to look at affect detection, as there's a lot of prior work on that, and a lot of progress that's also been made in terms of building affect detection models, especially with deep learning models. And we wanted to see again if that same trend emerges. But it's also, as we learned, that there are model structures, deep learning model structures that are intended to be untrained. So apparently this is in other contexts, this has been kind of recognized as maybe there is something here. So there are a couple of model structures that are meant to be untrained, essentially acting as random feature generators that can be used in other regression models. So we wanted to examine if a kind of model that's meant to be untrained does any better than maybe the untrained LSTMs that have been explored in some of the other works. And we also wanted to identify whether there's significant overlap in the features that are utilized by the trained and untrained models. Is it just the case that the untrained models have are wide enough, have enough parameters that we are just getting lucky and they're just randomly generating features that are ultimately learned by the trained model? And maybe we just need to have larger untrained random models and we'll get lucky every time and be able to use those instead of the trained models, because no one wants to spend hours training a model. So we wanted to see, is there actually overlap in the features that are being utilized by the two? Before going on, I'll kind of describe the prediction task of detecting student affect. So again, what we wanted to do here is utilize some of the prior work in this area. So the idea here is we have 4 labels of affect: engaged, concentration, boredom, confusion, and frustration, that are gathered from human observers who have gone into classrooms while students are interacting with a learning environment, in this case, assessments. And in this case, we can then take those labels, which are kind of gathered sporadically over time for each student, and we can pair them with the clickstream data that's collected from assessments in order to build these models. In which case, again, the task is basically over a student sequence. We have a sequence of clickstream level, action level data, and we want to, given that stream of actions, predict at certain time points. We want to predict what that student was maybe exhibiting at that time. And to do that, I'll also note that prior works have utilized a kind of 2 different feature sets. One was a set of 92 expert engineered features. But we also have seen in prior works that others have used just the raw clickstream level data, so just the actions and timestamps. And just to give an idea of how well the prior works have done at this task, we can see that the LSTM model using the raw features saw an AUC of 0.69, 695, and a relatively low kappa of 0.04. And the LSTM that was trained in, again, in prior work, these are both trained models utilizing the expert features, saw an AUC of 0.76 and a kappa of 1.7. But in any case, what we wanted to do again is see if we didn't train the lower part of that model and only train the output layer, how well could we get? And long story short, first result here, if we don't train those models, what we get is an LSTM using raw features got a 0.66 AUC, and actually higher kappa than the trained version using raw features. And then an LSTM using expert features, again, untrained, got a 0.7 AUC. So actually about, 0.06 off, 0.03 off, depending on which one you're looking at. So actually in the same ballpark in terms of performance, certainly well above chance. So again, this is already kind of lends itself to say that there might actually be something here that is interesting that's going on if we can get so close in terms of performance when we when we utilize these untrained models, which again took a fraction of the time to actually train, or I guess not train. Effectively, it's the same as just training a logistic regression. So looking at then, again, coming back to this idea, there are some other model structures that we wanted to examine in this work. There are a couple other, two, in fact, model structures that are meant to be untrained. And the first one that we examined was a bag of random embeddings, which basically takes a set of features or a sequence of features over time, multiplies that in projection matrix, and there are some kind of ideas of how you might structure that random projection matrix. So it's a kind of a pseudo-random projection matrix, and there's more detail in the paper on that. That basically generates this kind of high-dimensional feature vector for each of the time steps, kind of projecting it to a larger feature space, and then utilizing those features using a regression. So again, same idea as before, where we have this kind of random feature generation component, and then just training that output layer, a final regression on top of all that. And the other model structure that we looked at is an echo state network, which basically takes a set of features, throws them into this pool of randomly connected nodes. So it's very similar to a traditional neural network, only we kind of get rid of this layer structure, which nodes will be connected kind of randomly to each other within this pool. The idea here is that the features are kind of bounced around in this pool of random nodes, and then we can take a trained regression model and train it on the features that are kind of randomly generated within that network. In terms of evaluation, what we did is we took each of these three models. We looked again at the raw features and the expert engineered features as two different feature sets. And we're comparing this within a 5-fold cross-validation. But I will note that we're exploring different sets of hyperparameters for each model structure. So you'll note I'm going to be reporting kind of the best performing model that was generated for each of these. And what we did is we ran each model 5 different times with different random seeds within that cross-validation. So we are running a large number of models, and we're just averaging the model performance across these random seeds within the 5 folds. So that's important to note, because what we're trying to establish here is kind of what is the expected value of, or the expected performance of these random models. Although I will also finally note that even though we did kind of do this with 5 different random seeds, the performance of these untrained models didn't actually vary that much. So it wasn't the case that we got like a model that gave random chance one time and then performed really well the next time. They were pretty consistent in terms of the performance that they were giving, which was also kind of an interesting thought. And the evaluation itself is maybe a little bit confusing, and some of these models are maybe unfamiliar to you. I will note that all of the data and the code that we used is publicly available, and I'll give this link at the end as well. And it is in the paper as well. So feel free to take a look yourselves. So looking at these other model structures alongside that, the LSTM that I was talking about earlier, if we look at detecting affect, what we can see is the untrained models, again, pretty consistently perform reasonably well, again, well above chance, in some cases in the 0.7, 0.74 range. And what we can also see is that none of them quite outperform the trained models, which is maybe reassuring that training does actually get you something. But it's rather interesting that the untrained models come very close in terms of performance, certainly much closer than I originally thought would have been the case. And if we look at knowledge tracing, kind of replicating the prior work from Ding and Larson, and also looking at the trained versions from prior works, we see kind of a similar trend here, where we see the untrained models are not quite outperforming a lot of the prior works or the trained versions, but are coming very close to it. Close enough that if you were to kind of deploy this model, it might actually be very difficult to kind of tell the difference between the trained and untrained version, which again, maybe there's some utility there given how fast it is to train, or I guess, train the regression on top of these untrained feature generation components of the model. So again, the untrained models are almost as good as the trained counterparts. So the last piece that we want to do is just observe whether these models are actually utilizing an overlapping set of latent features. So what we did is we conducted an exploratory factor analysis looking at the trained and untrained LSTM model for affect detection to basically see are the learned features mapping onto the same set of kind of latent constructs or latent factors that are utilized when we are making the prediction. So what we did is we took all of the trained and untrained features that are spit out by the model, or the factors from the trained and the untrained model, and we just look at correlations. So we just look at Spearman's row, Spearman correlation, doing a kind of all pairwise comparison to see do any of the trained latent factors kind of look like the untrained latent factors. And what we just set an arbitrary threshold here, or rather relaxed threshold, which we set purposefully. A value above 0.6, we're saying suggests an overlap. We're saying that this feature is very similar to this other feature that's used by the trained model. And finally, what we see here, given a kind of LSTM at different sizes, when we have an untrained model at with 200 nodes, 400 nodes, etc., we're seeing actually that there's very little overlap, and that overlap doesn't seem to increase with the when we increase the size of our model. So when we add more hidden units to our model, we're not actually seeing a greater number of overlap. So we're not just kind of getting lucky and randomly generating features that are being learned by the trained model. We're actually seeing very little overlap, which suggests that there is maybe a couple of more just sequential features that are being utilized here that are giving it the performance that it needs. So in terms of just takeaways and just final thoughts, because it is, again, rather kind of surprising or unintuitive. So from that last analysis, we can kind of conclude that the trained models do learn different sets of features that lead to consistent improved performance, but only kind of marginal, which is a little surprising. They don't seem to lead to large improvements over the untrained features. So in this case, maybe there's some utility in using these untrained models in some way during to either better train other models, basically using them as additional feature generators. Maybe it's worthwhile to utilize these as kind of baseline comparison models. I hesitate to recommend using these models in practice, just because there is a large amount of randomness involved, and I think there's a lot of kind of misunderstanding around these untrained models. But again, I think there are some utilities, and if nothing else, I think that these can provide insights into what the trained models are actually learning and how they might be better utilized in application themselves.